Hello students, this is Vishwajeet Poddar, your chemistry faculty for NEET. And before I start, I would like to know about your state of preparation for your exam. On the scale of 1 to 3, how do you feel that your preparation is going on? This is Vishwajeet Poddar. I am basically a NEET faculty, NEET chemistry faculty, and currently with Altedemy. I have helped many students to clear their NEET examination, and I am with you. I hope you will take a lot of advantages to clear your NEET examination. Today, a topic that I have chosen for you to clarify, the topic is Lee-Chatelier's principle. This principle, you must have heard about it. And before I go ahead, I would like to know, are you ready with Altedemy to know the inside-out story of Lee-Chatelier's principle? Okay. Hello Rohini Pal. Are you ready? We can move ahead. Okay. First, let us talk about chemical equilibrium. Whenever we are talking about chemical equilibrium, the first thing that should come to our mind that it is basically a reversible reaction that we are always talking about. Reversible reaction. So it is basically a reversible reaction that is we are concerned about. What is the reversible reaction? Reversible reaction is generally a reaction which is moving in both that direction, and it is symbolized as, suppose A is one of the reactant, B is another reactant, we put a symbol like this which is a reversible, sign of reversibility, and we get C plus D. Chemical equilibrium situation comes only in a reversible reaction. And almost all the reactions, almost all the chemical reactions, if it is performed in a closed container, and at fixed temperature, if we do, it is most likely to be a reversible reaction. And second most important thing is, once a reversible reaction starts, it has to reach equilibrium. It will reach an equilibrium. So equilibrium in general is achieved in a reversible reaction when the rate of forward reaction is equal to rate of backward reaction. What do you say? Suppose this A plus B is getting converted into C plus D, and this is a forward rate constant. We write this as Kf. This is a constant pertaining to chemical kinetics. And suppose this is the backward rate reaction which we call as Kb. So we can say that rate of forward reaction is equal to Kf molar concentration of A and molar concentration of B. And similarly, we can write with rate of backward reaction as Kb, it is C and D. And equilibrium is a situation when Rf is equal to Rb. So we can write this as Kf A B is equal to Kb C into D, where the symbols have their usual meaning. This square bracket says molar concentration. So we can write that Kf upon KB, sorry, KF upon KB is equal to C, D, A and B. I'm sorry, whatever I was writing, I mean, I'm just sitting in front of that, but I have changed that place. So you can see this is basically what we are intending to let you know, that this is how we understand that equilibrium has achieved, and we quantify it. Kc is the equilibrium constant, Kf is the forward rate constant, Kb is the backward rate constant, and Cd in the numerator, A and B in denominator. C is molar concentration of C, I mean capital C, and capital D molar concentration of D divided by A into B. This is how we understand a chemical equilibrium. Now, let us understand that we have found out Kc for a particular reaction. Kc will just be a number. Kc will just be a number. Now, this number can always be put on a number line. Let us suppose equilibrium constant, when concentration terms are being used, is written as Kc and it stands here. And a reaction that was given A plus B, C plus D, it is at equilibrium. Rate of forward reaction is equal to rate of backward reaction. Now, suppose we wish to change any of the conditions bringing equilibrium. And what are those conditions which are bringing equilibrium? We can change the concentration, we can change the pressure, we can change the temperature, as well as we can change volume of the container. We can also add some kind of inert gases into this system. Inert gases. Putting some inert gas. A reaction was at equilibrium and we have placed some inert gases into the reaction system. These are the factors which can bring about some kind of alteration in chemical equilibrium state. Alteration. Always remember, Kc changes only when the temperature is changed. Only when the temperature is changed. With Kc, temperature is always associated. An equilibrium will be achieved at a particular temperature. As far as concentration, pressure, volume, inert gases are concerned, they alter the reaction. Temporarily it is altered. And then reaction starts moving in such a direction so that it achieves the equilibrium which was there at that particular temperature. Hello Mohan. I'm not telling what is there in NCERT, but there is nothing which you do not need to know in NCERT. You need to know a lot of things in NCERT, right? If you read NCERT very carefully, if you mug up the entire thing, whatever is there in NCERT, it is more than enough to clear your NEET examination. But then you will have to do it very carefully. You will have to understand a lot of fundamentals. Okay? Okay. Equilibrium, one important information that comes, that whether equilibrium is changed because of introduction of a catalyst or not. You should remember, suppose we are drawing a graph related to equilibrium and it is like this. It is an exothermic process. And if you are using a catalyst, what generally will happen when we are using a catalyst. If we are using a catalyst, this catalyst will be taking an alternative path and it will be like this only. There is no change in delta H when we are using catalyst in a reaction. There is no change in equilibrium constant when we are using a catalyst. But yes, there is change in what? Only the activation energy. There is change in activation energy. Neither delta H nor equilibrium constant, both are not changed because of the introduction of or presence of a catalyst in a reaction. To analyze all these changes, all these alteration, there are two scientists, Lee, Chatelier and Brown. They made generalizations to explain the influence of various factors on a system in equilibrium. The generalization is called Lee-Chatelier Principle. He has observed many reactions. Both of them have observed many reactions, and many of these reactions have basically helped them in generalizing this particular fact. If a chemical reaction at equilibrium is subjected to, is subjected to a change in pressure or temperature or concentration that govern the chemical equilibrium, the equilibrium position shifts in the direction in which this change is modified or reduced. I can put it another way, and I am putting it in a manner so that you can just memorize it. How do we write this? If a reaction is at equilibrium and we bring any change, into the factors, bringing equilibrium, then reaction shifts itself in a direction so as to nullify the effect. A reaction is at equilibrium, and equilibrium can be achieved by various factors. We need concentration, we need some kind of temperature, we need some kind of pressure, and the reaction has come to an equilibrium. And these factors, when it is changed, then reaction will always be shifting into a direction which nullifies its effect. And we will see to it one after another by changing different factors, and then you will see how these changes take place. If a reaction is at equilibrium and any of the conditions bringing equilibrium is changed, then the reaction shifts itself in a direction so as to nullify that effect. Hi Hania, we will explain you very shortly. Okay. Let us first talk about change of pressure. Let us take an example. Suppose we are taking a reaction like N2, this is gas, plus 3H2 gas. It is a reversible reaction. It becomes 2NH3. It is again gas. Suppose this is the reaction. And in this reaction, we can understand that pressure of gases is more on reactant side. Pressure of gas is more on reactant side. More number of moles in gaseous state means more pressure. Less number of moles, less pressure. As we can observe that on the reactant side we have 4 moles of gases. On the product side we have 2 moles of gaseous element. Naturally, pressure is directly related to number of moles. So we can say reactant sides are having more pressure, product side is having less pressure. Now, if we increase pressure in this situation, if we increase pressure, this reaction has come to an equilibrium in a container, and if this reaction is subjected to more of pressure, so let us try to observe what will happen. We always told you reaction will always be shifting in a direction so as to nullify the effect. Now on the reactant side there is always a more pressure in this reaction. On the product side there is less pressure. So obviously reaction will be shifting towards what? Reaction will be shifting towards product side. And what will it mean when the reaction will be shifting towards product side? That means more of NH3 production will start taking place. More of NH3 production will start taking place. And that gives us an idea. Suppose industrially we want to prepare more of NH3, then the reaction, this is a Haber's process, this reaction has to be performed at high pressure. High pressure. So one of the conditions is high pressure. But it's not always necessary that in each of the reactions such kind of situation can happen. We can take another example. One is like 2HI gas gives H2 gas and I2 gas. Suppose this is the reaction. Now here we can observe both reactant and product side have got similar degree of pressure. Here there are 2 on the productant side 2 moles. Here on the reactant side there are 2 moles. So changing of pressure brings no change, no effect onto such kind of reaction. So it is useless to go about more of pressure or less of pressure or something like that. We can take another example. Suppose we say PCl5 gas gives PCl3 gas and Cl2 gas. Are you understanding? Rohini, Mohan Reddy, Rayan, Hania? Okay, you can send me the fillers. Suppose we are taking another reaction, that is PCl5, all in gaseous state. Now on the product side here we can see there is more pressure. Reactant side it is less pressure. If we are increasing pressure onto this system, if pressure is increased, then obviously reactant side have got less pressure, the reaction will be moving towards the reactant side. And if the reaction will be moving towards reactant side, if we increase the pressure, more of PCl5 will start getting produced. Less of PCl3 and Cl2 will be produced. So this is how the things can be summarized, like change in pressure has effect on equilibria involving gaseous substances, and there is change in total number of moles of gaseous reactant and products. An increase in pressure on a system at equilibrium will shift the equilibrium in the direction in which pressure is reduced or decrease in number of moles is observed. I hope you must have understood it by 3 different kind of example, where in 3 different kind of example delta Ng is different. Notice it. This is very important concept, important factor. Here if you write delta Ng is -2 Here if you write for HI, the delta Ng is equal to 0, and for this particular reaction delta Ng is positive. Delta Ng is positive. So depending upon whether delta Ng is positive, negative or 0, delta Ng means number of moles of product in gaseous state minus number of moles of reactant in gaseous state. As the pressure of gaseous system is increased, the volume occupied the system decreases. We know that if pressure is increased, volume is decreased, so that the total number of moles per unit volume increases. Right? About this we will be looking into it very shortly. Pressure has no effect on equilibria in solid, liquid and solution state. If the substance is either in solid, liquid or solution state, the change of pressure has no effect onto it. Even in the gaseous state, if there is no change in number of moles of gaseous reactant and products, pressure has no effect on the equilibrium. Right? If there is no change in number of moles, as I told you, delta Ng is 0 of gaseous reactant and product, pressure has no effect on equilibrium. Delta Ng is very important. We generally ignore solid and liquid reactant and product substances. For solid and for liquid, pure liquid, for solid and for pure liquid, we take concentration as 1, or we say unity. For solid as well as for pure liquid, we take concentration as unity or 1. Okay. Coming to temperature, very important. The first thing, we know that we have two different types of reaction. One is exothermic and another is called as endothermic. Exothermic and endothermic reactions are there. Exothermic reactions are generally represented as this. Endothermic reactions will generally be represented like this. This is exo and this is endo. Right? Exothermic reactions, general representation. Exothermic, in which heat is being liberated. Endothermic, those reactions in which heat is being absorbed. Now, if forward reaction is exothermic, forward reaction is exothermic, obviously the backward reaction is endothermic. Right? If forward reaction is exothermic, backward reaction is endothermic. We should bear in mind. You can see here the nature of this graph and nature of this graph are just opposite to each other. So if we take an exothermic reaction, suppose A plus B gives us C plus D and delta H is having a negative value, which indicates it's an exothermic process. If we increase the temperature, now look here, for an exothermic, if we are increasing the temperature, what will happen? Forward reaction is already exothermic, but backward reaction is endothermic, where heat is being absorbed. So for an exothermic reaction, if we are increasing the temperature, obviously the reaction will start moving in a backward direction. So for an exothermic, it is never advisable to go for an increased amount of heating or temperature. For an exothermic reaction, we always use low temperature. It should be working on low temperature. Exothermic reactions should also work on low temperature. But yes, we should bear in mind, what does low temperature means? Minus or 0 degree centigrade? It's not always there. We need at least the activation energy. So it will depend upon reaction to reaction what can be categorized as low temperature for a particular reaction. Right? Same is the case if a reaction is endothermic. If A plus B, C plus D, and delta H is positive. Suppose this is the situation. Endothermic process. So forward reaction is endothermic. If you increase temperature, obviously it will be moving in forward direction. So for an endothermic reaction, to make the reaction move in forward direction, we can increase the temperature or we can conduct the reaction at higher temperature. In general, the temperature dependence of equilibrium or equilibrium constant depends on the size of, rather enthalpy of reaction. Very important point. I have also told you that equilibrium constant changes only with temperature. And suppose we have a temperature T1 at which equilibrium constant is K1, and we have a temperature called T2 at which equilibrium constant is K2, and T2 is greater than T1. Suppose this is the condition. As I have told you, equilibrium constant changes with temperature. Suppose at temperature T1 we have equilibrium constant K1, and temperature T2 we have equilibrium constant K2, and T2 is greater than K1. In this situation, K2 will be greater than K1 if reaction is endothermic. And K2 will be less than K1 if reaction is exothermic. K2 will be less than K1 if reaction is exothermic. And same thing has been written out here. Equilibrium constant for the reaction with positive, that is endothermic positive sign, increases with an increase in temperature. Equilibrium constant for the reaction with a negative decreases with an increase in temperature. The temperature affects a reaction in two ways. It increases the rates of reaction so that the equilibrium is reached earlier, and it affects the equilibrium constant. Both the things is done by increasing the temperature. Let us come to concentration. Suppose for the same reaction A plus B, C plus D, suppose we have an equilibrium constant, this is Kc, and on the number line Kc stands here. Let us suppose like this. So equilibrium constant will be written as C D A B. Now in this situation, just imagine if concentration of product is increased. Right? If we are increasing the concentration of product, what will happen? Temporarily, Kc will be shifting to this place. Let us call this as QC. we have increased the concentration of C and D, what will happen? Equilibrium will be temporarily shifted to QC. Now it will always try to achieve this old equilibrium. So obviously the reaction will start moving in backward direction. So increasing the concentration for a particular chemical reaction is never advisable. Rather, you must have noticed it somewhere that as soon as some product is being made, we generally try to filter it out so that the reaction starts working very smoothly. And similarly, we can do it. Suppose concentration of reactant is increased. Reactant is increased. Now when we are increasing the concentration of reactant, denominator is being increased. In that situation, a new case QC will be here. Now in this situation, the reaction will start moving in the forward direction. So this is how we are analyzing the entire reaction and understanding the concentration change of the reactant. The concentration stress of an added reactant or product is relieved by the net reaction in the direction that consumes the added substance. Though it has been written technically, but you can understand how we have tried to make you understand. The concentration stress of a removed reactant or product is relieved by the net reaction in the direction that replenishes the removed substances. So that is what I want to say, that if in a reaction, product is filtered out in the process of the reaction, that means you are decreasing the concentration of product. And when we are decreasing the concentration of product, we are compelling the reaction to move faster in the forward direction. That means more and more of product should be or can be created, right? The same thing has been mentioned here. What is the effect of change of concentration? Same thing, whatever I explained you, it has been written out here. Unlike law of mass action, Lee-Chatelier principle can be applied to all equilibria: physical, chemical, homogeneous and heterogeneous equilibria. It is very important as statement. Chemical equilibrium or Lee-Chatelier principle can be applied in any such situation: physical, chemical, homogeneous and heterogeneous equilibrium, all. Well, increase of the external pressure on the reaction at equilibrium favors the reaction in the direction in which the number of mole is decreased. Increase in temperature of the reaction at equilibrium favors that reaction in which heat is absorbed. That is what we have just mentioned. Increase of concentration of reactant in the reaction mixture at equilibrium favors the reaction in the forward direction, and decrease of concentration of product in the reaction mixture at equilibrium also favors the reaction in forward direction. It is just the repetition of the kind of thing that we have said. What is the effect of a catalyst? Look here. Catalyst has no influence on the equilibrium. This is because catalyst favors the rate of forward and rate of backward reaction equally. That is why there is no change in equilibrium. Okay, let us talk about effect of change in volume. Though it is very sketchy to understand the effect of change in volume, but you can easily understand it by this way. You can always associate. Suppose we have taken the same reaction, N2 plus 3H2 is giving us 2NH3, and we know, suppose in this particular reaction, volume of the container is increased. Volume of the container is increased. And how have you to handle such situation? Just try to understand. You must have noticed, understanding or analyzing pressure is easy because pressure is directly related to number of moles. Okay. Now, if the volume of the container is increased, can we think of what will be the effect on pressure? If the volume is increased, pressure will be decreased. We should always try to analyze this way. increase of volume, that means if we are performing the equilibrium reaction in a smaller container and then we have shifted it to a larger container, that is how we can say the volume has been increased, right? Like it is quite possible that you perform an equilibrium in this big a container, and it is also possible that you perform this equilibrium in this big a container. Will there be a change into equilibrium? That is what we are trying to analyze. In a smaller container and in a larger container, when we are shifting from a smaller to larger, we are increasing the volume. And increasing the volume is equivalent to decreasing the pressure. So you have to analyze what will happen if we will decrease the pressure. What will happen to this situation when we will decrease the pressure? If we are decreasing the pressure, then obviously reaction will be moving towards that direction where it has more pressure. Where lies the more pressure? It lies on the reactant side. Reactant side, we have more pressure, isn't it? So it will happen that the reaction will start moving towards the direction of the reactant, not of the product, right? An increase in pressure means a decrease in volume. Increase in pressure means decrease in volume. Okay, let us look at a situation when we are adding an inert gas. Adding an inert gas. What will happen when we will add an inert gas to a reaction equilibrium? Addition of inert gas can be done by two ways. Number one, at constant volume. At constant volume. And secondly, at constant pressure. At constant pressure. Look, if we are adding an inert gas, it is not interfering with the usual reaction that is going on. Suppose you put an inert gas in this particular reaction, N2,3H2, 2NH3, the inert gas is not going to interfere it anywhere. Inert gas is not going to interfere it anywhere. And secondly, we have also put a condition that the volume is also not going to change. Inert gas, addition of an inert gas can take place at constant volume and at constant pressure. Suppose we are adding inert gas at constant volume. So if we are adding an inert gas at constant volume, no change in concentration. No change in concentration. And if there is no change in concentration, in this situation, no change in equilibrium constant. No change in equilibrium constant. But if we are adding inert gas at constant pressure, now pressure has to be kept constant. Pressure has to be kept constant. And we are adding inert gas. That means we are increasing volume. That we are increasing volume. I hope you are getting it. If we are adding inert gas at constant pressure, that means it is equivalent to increasing volume of the system. Increasing volume of the reaction container. Now, we have already analyzed what generally will happen in case of increasing volume. If we have such reaction where delta Ng is positive, we have a situation where delta Ng is negative, we have a situation where delta Ng is 0. We can analyze this by doing the same thing, increasing volume. When an inert gas is added to the system of equilibrium at constant pressure, the total volume will increase. The concentration of the substance decreases. The equilibrium will shift in a direction in which there is increase in the number of moles of gases. So it will depend upon the reaction in which direction it will be moving. Well, what are the applications of Haber synthesis? Chemical equations denoting the synthesis of ammonia from its element is number of moles of gases. By observing the equation underlying the reaction, it can be noticed that the Haber synthesis is a gas phase reaction. We are talking about this particular reaction, which is a Haber situation. Suppose this is a reaction. Now you can clearly understand, if we are increasing pressure, what will happen? Reaction will start moving in forward direction. I hope you can understand that. Because if it will be moving in forward direction, it will be nullifying the pressure. Suppose we are increasing temperature. Since it is an exothermic reaction, if we are increasing temperature, reaction will start moving in backward direction. Because backward process is endothermic process. Third, increasing volume. Suppose volume is increased. Volume increase means decreasing pressure. So if we are decreasing pressure, the reaction will start moving in a direction where more of pressure is there. So it will start moving in backward direction. Look at this situation. Increasing volume means decreasing pressure. If we are decreasing the pressure, then obviously the reaction will start moving in the backward direction, because backward direction has more pressure and forward direction has got less pressure. Already you are increasing the pressure. You are already decreasing the pressure. If we are increasing the pressure, then it is moving in forward direction. If we are increasing volume means decreasing pressure. Obviously, it will come as a natural corollary for the first statement. So pressure, volume, temperature, three things have been taken place, and you can understand adding inert gas at constant pressure. Now look what will happen. If we are adding inert gas at constant pressure, what will happen? Volume has increased. Now increasing volume is equivalent to decreasing pressure. So it will start moving in backward direction. This is how we interpret the things. The one and the same thing has been said. 4 moles of reactant produce 2 moles of product in Haber synthesis. The reaction is associated with the decrease in volume. Since the mole is decreased, high pressure must favor the formation of ammonia. If we are increasing pressure, then obviously reaction will start moving in forward direction. Okay, before I move ahead, we should talk about our Telegram channel of Altedemy. If you are joining the Telegram channel of Altedemy, we have plenty of PDF materials. We have plenty of free classes. We have a lot of announcements that keep on coming. We have discounts and prizes, all those things you get. Well, it can be analyzed to see the formation of ammonia is exothermic. It is actually. If heat is supplied, ammonia absorbs energy and decomposes to give its element. Hence, Chatelier Principle predicts low temperature as favorable formation. However, moderate temperature is used experimentally as the reaction is slow at low temperature. So this is how we handle temperature when a reaction is Haber's process or Haber's process. Increase in the concentration of reactant must favor the forward reaction. The reaction is to be performed at high pressure, hence pumping more reactant gases into the vessel is inconvenient. On the other hand, ammonia is removed from the vessel from time to time, favoring the formation of more ammonia. As I suggested, we will have to keep on removing ammonia as we produce it. Well, introducing catalyst also we have understood. And as a matter of generalization, in Haber's process, about which you have to study, optimum condition for Haber synthesis, high pressure, almost around 200 to 250 atmosphere, moderate temperature 725 to 775 Kelvin, removal of ammonia by liquefaction, and use of iron as catalyst and molybdenum or mixture of K2O or Al2O3 as promoter. These are the usual conditions of Haber's process of formation of ammonia. We can take up another example also. We are taking up another example of a reaction. 2SO2 plus O2 gives 2SO3. Delta H is minus 189 kilojoule. Here you can see delta Ng is equal to minus 1. Minus 1. The underlying equilibrium chemical reaction in the commercial production of sulfuric acid is the oxidation of sulfuric acid. You know that there is a process called as contact process. In contact process, we produce H2SO4. And this is the key reaction in contact process. This is the key reaction in contact process. We take sulfur dioxide, rather we take sulfur, we do the combustion, we form SO2. SO2 is taken in the presence of O2 and it forms SO3. And with SO3, we use H2SO4 to get H2S2O7, which is oleum. And when H2S2O7 is diluted, we get twice the molecule of H2SO. This is the entire contact process. And in this contact process, we have this reaction about which we are analyzing the equilibrium. It can be noticed that the main reaction in the contact process is a gas phase reaction, a reversible reaction. It is basically a reversible reaction. We could just not put an exothermic reaction, and a reaction in which the number of moles of the product is less than that of the reactant. The forward reaction leading to the formation of sulfur trioxide is a reaction involving decrease in the number of moles and hence decrease in the volume. Hence, high pressure favors the forward reaction based on Lee-Chatelier principle. If for this particular reaction we will be applying high pressure, then the reaction will be moving in the forward direction, right? Well, the reaction leading to the formation of sulfur trioxide is exothermic. So according to the prediction of Lee-Chatelier, low temperature favors the forward reaction, but at low temperature the rate of the reaction is less. Therefore, moderate temperature like 673 Kelvin is used for the contact process. Okay. Coming to removal of sulfur trioxide from time to time from the reaction mixture favors the formation of more sulfur trioxide. Sulfur trioxide can be removed from the reaction mixture by absorption into concentrated sulfuric acid, forming oleum, which is subsequently diluted to give sulfuric acid. As I told you, as I shown you, that in the process of formation of H2SO4, we basically form oleum and then we add water to it and then create it. So contact process has high value of, but the reaction between covalent substances is slow. Hence, use of catalyst can speed up the reaction and make the attainment of equilibrium fast. So we use generally a catalyst and do the reaction fast. Well, subscribe Altedemy as fast as possible. You will get free classes regularly. You will come to know about a lot of things. Optimum conditions for the manufacture of sulfuric acid by contact process are slightly high pressure, 1.5 to 1.6 atmosphere, slightly high pressure, moderate temperature, that is 650 to 700 Kelvin, and removal of sulfur trioxide by absorption into H2SO4, and use of vanadium pentoxide, this is called as V2O5, or platinized asbestos, PT. This is a favorable condition for it. Carriage of oxygen by hemoglobin in blood is given by the equation involving the heterogeneous equation. Well, look here, we have a reaction. Carrying of oxygen by hemoglobin, HB stands for hemoglobin, and it is carrying oxygen. It is given by this heterogeneous equilibria. The blood that is in equilibrium with oxygen of the air in the lungs find a situation in the tissues where the partial pressure of oxygen is low. According to Lee Chatelier, the equilibrium shifts to left such that oxyhemoglobin changes to hemoglobin, giving up the oxygen. When blood returns to the lungs, the partial pressure of oxygen is higher and favors the formation of more oxyhemoglobin. Same principle is being applied. Same principle is being applied. Even evaporation of water in a closed vessel is shown by a heterogeneous equilibrium, H2O liquid to H2O gas. This process occurs by the absorption of heat. Hence, high temperature is favorable for producing more water vapor. The process of producing water vapor involves an increase in the number of moles from 0 to 1, and based on the Lee Chatelier principle, low pressure is predicted as a favorable condition in such situation. Well, solubility of ammonium chloride increases while that of calcium chloride decreases upon heating. Can you suggest why does it happen? We can apply Lee Chatelier principle to find this out, right? Okay, that brings an end to our session for this particular course. And before I close down this session, we would like to let you know about our courses, our program, and would like to give you a very handsome offer if you can avail it as fast as possible. Well, our courses generally comprise a lot of classes. 90 plus classes we have mentioned, but actually it comes out to 120 plus classes. It's a very convenient educational platform. You will find it enjoying as you are enjoying. You will get syllabus from NEET experts. We have flipped classroom methods. We have doubt solving practice and many other such features you will find once you join. And how our classes look like. You get plenty of theory. You get plenty of study materials. You get webinars. We get a lot of homework and we get your homework checked. This is how the situations are coming. We have come out with various different programs and we have categorized our programs into 3 different sections. That is light program, smart program and proficient program. In a light program, we have interactive live classes. We have structured courses and PDF. We have live tests. We have physical notes. In our smart program, along with all those 4 features, we have the features of one-to-one mentorship. We have live doubt solving program and we are conducting mock tests regularly. In the proficient program, we have interactive live classes, structured courses and PDF, live tests, physical notes, one-to-one mentorship, live doubt solving program, mock tests regularly, as well as additional special courses. You can choose to join our smart course and I am giving you an offer that is Chem NEET 30. This is my promo code. If you avail this, you can get all these things at a special price of rupees just 299 for a month. Don't delay. Join it immediately. See you soon. Thank you very much.